Greetings. Uh, my name is KVL Subramaniam, and I'm going to talk about fracture and shear behavior of recycled aggregate concrete. Before I proceed, I would like to acknowledge the support of my PhD student, Saurabh Chakrabarti, whose work I'm presenting here. The basic idea of this work is to investigate the fracture behavior in concrete containing recycled concrete aggregate, and we try to relate it to the shear behavior of reinforced concrete containing recycled concrete aggregate. So the outline of the talk is very straightforward. First, talk about the motivation for using recycled concrete aggregate. Then I would talk about the fracture response of concrete containing recycled concrete aggregate, and shear behavior of concrete with this recycled concrete aggregate. So the recycled concrete aggregate is also referred to as RCA. RCA refers to recycled concrete aggregate. Now, the motivation for the work is very straightforward. Now, primarily, demolition of old structures are inevitable. As structures fall into disuse, they are dismantled, they are discarded, and they are essentially demolished. Now, there is a need to dump or the waste material, and currently, the rate at which the landfills are filling up, filling of landfills with this construction debris is no longer an option. So there is a need to recycle whatever is coming out of old buildings. Then the other thing is aggregate come from natural sources, and extracting natural aggregate for concrete construction typically extracts a heavy environmental toll. So there is a lot of the activity of stone production is associated with destroying of natural habitat. There is deforestation often accompanying that, and soil erosion that accompanies the extraction of aggregate. And this is what is forcing us to look for alternatives to aggregate. So there is the issue of depletion of natural resources. We're also running out of stock of good aggregate, good stone that we can use as aggregate. On the other hand, we have a piling problem of demolition debris that has to be used in a safe manner. So resource depletion and waste utilization are driving this demand for recycled concrete aggregate. Now, the other part of motivation, which is India specific, comes from the fact that India is the third largest consumer of aggregate, and we are the second in global aggregate production. So if you look at the chart here, you see that we are amongst the right now currently we are the second largest aggregate producer, and most of our aggregate go into making concrete or into making bituminous concrete. Now, there is also concurrently an increasing demand for construction, and to meet this demand, I have to produce aggregate. So already there's a large eco tag associated with the production of aggregate, the natural aggregate, and therefore we have to start looking at recycling because the natural aggregate are a non-renewable resource. So this is a very powerful motivation for us to start looking at alternatives to the use of natural aggregate and promoting the use of RCA. So therefore, we are looking at this RCA as a sustainable building material, which will allow us to sustain the production of over a longer term rather than relying solely on the natural aggregate. Now, what is recycled concrete aggregate? After demolition of concrete, there are other construction material like wood, steel, and brick, which are also mixed up in the debris, and these have to be removed. Then, after proper gradation, we end up with recycled concrete aggregate. And it, of course, recycled concrete aggregate is primarily made up of the natural coarse aggregate. This is the parent aggregate that went into making the old concrete, and it's often surrounded by the old mortar. So this is the old mortar that sticks to the old aggregate. This is what is left after the demolition process, after we demolish an old concrete structure. So the RCA that we have is a complex material. It has an aggregate phase. The aggregate phase is that of the parent aggregate that went into the old concrete, and the mortar phase is the old mortar that surrounds the aggregate phase. Now, when we place this RCA in fresh mortar matrix, or if you make concrete with it, what happens is that now we end up with creating new interface. So here, if this is the new cement mortar into which I placed the RCA, I create a new ITZ here, which is the ITZ between the new mortar and the old mortar. I also create another ITZ wherever the old parent aggregate comes in contact with the new cement mortar. And in addition to that, I have the old ITZ. This is the ITZ between the parent phase, aggregate phase, and the parent mortar phase. So basically, the RCA, as I'm using it, brings with it this old ITZ, which is between the natural course aggregate and the old mortar phase. But the minute I make concrete out of it, I create two additional interfaces, which is the new ITZ between the new mortar and the old mortar, and the new ITZ between the old parent aggregate phase and the new mortar. Now, the methods of production of this RCA have varied, but typically they have come from demolition of buildings. A lot of work that has been reported, at least in literature, the concrete RCA that's been used comes from tested lab specimens. And a lot of these labs, a lot of concrete is tested, and often this concrete is then crushed and made into aggregate. Then the broken pavement and bridge decks and other transportation structures account for the remaining part of the sources that make up the RCA. Now, when one goes into demolition of building, one has to be careful because oftentimes the RCA gets contaminated with a lot of other building material like brick and sometimes also steel. So if you look at the production of the RCA, recycled concrete aggregate, usually we start with large blocks of concrete, which are then crushed using in a jaw crusher. A magnetic separator is used to separate out any iron scrap. Then, of course, it's put into a vibrating screen. And from there, we segregate based on sizes. And if any large particles are left, they're then put into an impact crusher and reduced in size. So now coming to the general properties of recycled concrete aggregate. The most important things that have been reported in the literature pertain to specific gravity and bulk density. And we have water absorption and the abrasion test, the crushing value or the impact value of this aggregate. These become important. And these are the measures that basically separate the RCA from a natural aggregate. Now, and these have tremendous impact on the mechanical and durability properties of concrete. Therefore, these have to be evaluated. So let's see. Now, coming to specific gravity and bulk density, typical natural aggregate that's used has an oven dry density going from 2300 to 2900 kilogram per cubic meter. But when we talk about RCA, this is concrete, the aggregate that has been derived by crushing of concrete. The oven dry density is lower. It ranges from 1830 to 2030. It's actually a lower value. And the reason for the lower value is because of the mortar that is attached to the coarse aggregate. So if you look at a typical RCA, there's a mortar fraction. This is the mortar fraction from the parent concrete that is attached to the aggregate. And this mortar fraction is less dense and more porous compared to the aggregate phase. And as a consequence, the dry density becomes much smaller for RCA compared to regular aggregate. Now, this problem gets compounded when we go to fine aggregate. As the aggregate size decreases, the adhered mortar content as a percentage of the total mass or total volume of the aggregate increases. And as a consequence, once we get into the fine aggregate phase, the mortar fraction, because of the increase in mortar fraction, this discrepancy between the natural aggregate and the coarse and the RCA becomes even larger. So now coming to water absorption, typical water absorption of aggregate ranges from 0.5 to 1.5%. There are natural aggregate, which do have higher absorption, but normal range that we encounter is in between half and 1.5%. However, the recycled concrete aggregate can have an absorption, a water absorption as high as 15%. And this again has to do with the presence of that porous adhered mortar on the aggregate face. And occasionally we also get foreign material like brick, which contribute to additional absorption. But one has to prepare for a much higher water absorption with RCA. Now, here's a chart which relates the oven dry density to the water absorption. And you can see As the oven dry density decreases, the water absorption increases. That's because the motor fraction in the aggregate increases. The abrasion test, which tells us how strong the aggregate is, tells the RCA is typically weaker compared to natural aggregate. This has to do with the old mortar that is adhered to the aggregate phase. This is usually the weakest link in the RCA, and or at least this is thought of as the weakest link. And the higher the amount of adhered mortar, lower is the resistance of RCA to fragmentation. So typically we get lower crushing values. A limit of 30% is set in the standards for the RCA to be acceptable for use in structural concrete. Coming to compressive strength, RCA, when I replace natural aggregate with concrete, it can produce a strength as low as 30% lower than the regular concrete. And again, the blame falls on the interface between the old and the new mortar, which is considered to be the weak phase. And usually that results in a larger number of cracks in the case of concrete containing RCA. But here there's a split. So depending upon the grade of concrete that I'm using, if I'm using a lower grade concrete, then typically the strength of mortar decides the strength of the concrete. So here the mortar is weaker than the aggregate, so it's the strength of the mortar that decides. And so it has been observed, at least as far as compression goes in lower grade concrete, replacing a natural aggregate with RCA gives almost comparable compressive strength. However, once we go to higher grade concrete, because now the aggregate becomes the weaker phase, here it is said that the strength, the drop in the performance, at least in strength, is observed. Coming to elastic modulus, again with the use of RCA, the elastic modulus is lower. Here's a chart that shows that as I progressively increase the RCA dosage, going from 0, which is natural aggregate, to 100%, which is complete replacement of natural aggregate with RCA, there is a drop in the elastic modulus. And this again is is because of the old mortar, which is less stiffer than the aggregate phase within the RCA. Tensile strength, again, we see a decrease in the tensile strength. Up to 30% decrease in tensile strength has been reported. And factors which affect the tensile strength include the residual mortar content, the type of mix, whether it's a high strength or a low strength mix, and the method of replacement that we use. Method of replacement, typically people do a by mass replacement. Now there are other procedures that are suggested, which allow for a replacement based on the aggregate phase in the RCA, which have been known to produce comparable strengths. Finally, coming to fracture properties, there is a decrease in the fracture energy of concrete containing RCA, and this has been related to the porosity. The porosity, if you look at the graph here, the calculated fracture energy related to porosity, there's a decrease with an increase in the porosity. And the increase in the porosity is related to RCA. So when RCA is placed in concrete, it results in an increase in the porosity, particularly around the aggregate, where the new mortar sits around the aggregate, the ITZ between the RCA and the new mortar. And that has been found to be a source for the decrease in the fracture energy of concrete containing RCA. So here are the things that come up as a research gap. First thing is understanding the tensile cracking and fracture in RCA. We need to get a proper understanding and understand the influence of the matrix strength on the fracture response in concrete with RCA. Then linking the fracture behavior, the structural response in shear. So reason why shear becomes important, because shear behavior of concrete is driven by the growth of a crack in concrete. And the response, the resistance of reinforced concrete to shear is primarily derived from the aggregate interlock, the stress carrying ability of a cracked interface, and the total capacity, the shear capacity of reinforced concrete. A large, significant portion of it comes from this shear transferability or the transfer capacity of concrete across a cracked interface, across a shear crack. So therefore, it becomes important for us to understand the role of fracture to see what kind of cracking, if there is a change in cracking, and how that would influence the shear behavior. So next, I'll present the results on the experimental study. Here we sourced we had natural aggregate, and the properties of the natural aggregate are given. They were taken in two size fractions, 20 mm and 10 mm. And we also sourced recycled concrete aggregate. Here are the properties. You can see that the RCA have much higher water absorption. As you see here, for the 10 mm, the water absorption is 0.3, whereas for the 10 mm RCA, it's 6.88, much higher. And what else you notice is that the water absorption increases as I decrease the size. This goes to what has already been observed. The impact value, which tells us how strong the aggregate is. The impact value of the 20 mm RCA is 13.73, whereas by the time I come to 10 mm RCA, because it has a much larger motor fraction, its impact value is 25.27. It's a weaker aggregate. So with this, before we started using this RCA in concrete, a section was taken across the RCA just to understand the nature of the interfaces that we have in this RCA. So here is a micrograph of RCA, which shows the aggregate phase and the attached motor phase. This is the ITZ between the aggregate phase in the existing RCA. So this is the aggregate in the parent aggregate phase, and this is the parent motor phase, the attached motor. And you can see that this interface is actually very dense. It is actually very nicely packed. So it's actually quite a strong interface where the two materials are bonded together. And this interface has survived the rough and tough process that is used to produce the RCA. It has survived the process of breaking the concrete, crushing it. And so therefore, you can see that this is actually not such a weak link. The material is very nicely packed. There are no signs of apparent weakness along this particular interface. So we started with the fracture testing. For that, we designed a concrete mix with a characteristic strength, compressive strength of 30 megapascal. And this is a typical mix design. So this is the mix design that we used with normal aggregate. And the same mix design was used, except the coarse aggregate in the 20 and the 10 mm size ranges were replaced with RCA. So that we had now two concrete mixtures. One which was designed with normal aggregate, another one which is designed with recycled concrete aggregate. But all other ingredients essentially remain the same. And the concrete itself was basically produced for a characteristic strength of 30 MPa, and of course, a target mean strength of 38.25 MPa. Now, just to show you the the compressive strength that we got on progressive replacement of natural aggregate with the RCA. So this is the parent concrete. This is the concrete that was made using natural aggregate. This is M30 grade concrete, and we got a mean strength of 42.8. And as we increase the replacement level going from 0% to 100%, then there's a steady decrease in the compressive strength, and we got a compressive strength of 36.6 on using only RCA in making the concrete with the same mix proportion. What is shown here in the graph is the load versus CMOD curve. This is the fracture test response. So to get this fracture test response, if I just go here in the previous slide. So this a concrete beam is tested in 3-point bending configuration. A notch is cut in the beam, and we have a CMOD, crack mouth opening displacement gauge, that is placed across the notch. And slowly that notch is opened by controlling the movement of this loading point here on this beam. So this is the load response that we got from the fracture test, the load versus CMOD. The outermost line, the black line here, is for the control concrete, which is made up of natural aggregate. And with progressive increase in RCA replacement, we see a progressive decrease in the peak load on the fracture response. The overall shape looks the same. And the interesting thing is up to 30% replacement, in fact, there's not much of a change. But after that, you can see that there is a continuous decrease in the peak load. Now, if I was to look at the area under the curve, which gives me the fracture energy, we can also see that there's a decrease in the fracture energy with increasing replacement level of RCA in the mix. So if I look at M30 0%, which is made totally with natural aggregate, and M30 100%, which is made with 100% replacement with RCA, we can clearly see that there is quite a large difference in the load response here, in the fracture test response. Next, I want to introduce this crack hinge model. The crack hinge model is basically an idealized representation of a beam with a crack. Now, when we have a concrete beam that is loaded in 3-point bending, and a crack forms here, an area close to the crack behaves like a hinge. And this hinge behavior is dominated by the behavior of a crack. So with this representation of this cracked element as a hinge, and assuming that the stress transfer with the crack follows a cohesive relationship, which is a stress versus crack opening relationship, one can actually predict the load response of the concrete beam for different crack lengths. And that is what was done. And so here what I'm showing you is a match. So we took a typical load response of a beam, and here we basically reproduced or tried to replicate that response by this analytical prediction that we get from the hinged crack model. And when I match the analytical prediction with the experimental response, from there I can back out this cohesive behavior. Cohesive behavior is the stress, the crack closing stress as a function of crack opening. So as this intercept here basically is the normalized stress, the stress has been normalized to the tensile strength. So this is the point at which the crack is initiated. Now, as the crack is opened and as the crack opening starts becoming larger and larger, the stress transfer that is taking place across the crack starts decreasing. This relationship between the stress and the crack opening, this relationship is called the cohesive stress relationship. So we are able to extract the cohesive stress relationship of concrete undergoing crack growth or for the crack growth using this crack hinge model that I presented in the previous slide. Now, from the crack hinge model, I can also extract the tensile strength of concrete. And tensile strength is a very difficult property to measure. But from the crack hinge model, we can actually extract the value of tensile strength. And the tensile strength is listed here. So we see that for the concrete totally made of natural aggregate, we get a tensile strength of 2.39 MPa. But by the time I go to 100% replacement, the tensile strength decreases to about 2.07. So there is actually a steady decrease in the tensile strength as I'm replacing the normal aggregate with RCA. Now, the other thing is this cohesive stress. So the cohesive stress that we got from the different concretes which contain different replacement levels are plotted here. The top blue line here is the cohesive stress that we get for concrete made with natural aggregate, and the other lines show the cohesive stress for concrete made with different levels of replacement. The dotted red line shows the cohesive stress that we get for 100% replacement or concrete that is entirely made of RCA. And here on the right hand side, I'm showing you a zoom of this early part of the response and only keeping the concrete made with natural aggregate and concrete made with RCA. And you can see that if you look at the cohesive stress response, this is the stress at which it's cracking. And of course, it's a normalized stress, so it always has an intercept of 1. As I start increasing the crack opening, clearly the natural concrete that is made with natural aggregate is able to transfer a higher stress value. So if let's say, look at a crack opening, then the stress transfer taking place across the concrete made with natural aggregate is higher. So the decay or the decrease in the stress carrying ability with increasing crack opening is actually much faster for RCA concrete when I put RCA into or recycled concrete aggregate into in concrete. And so this basically indicates an increasing brittleness of the material. I have a much more rapid decrease in stress. Stress decays very rapidly as I start opening the crack. Now, of course, if it's ideally brittle, then I will get a drop that goes from 1 to 0. So the reason I get a steady decrease is because this is a quasi-brittle material. But even here, if I look at comparing these two, the indication is that this RCA makes the concrete a lot more brittle. We also measured the surface area. So surface area was calculated. This is the true surface area of the fracture that is created. So here is the concrete beam. This is after it has been fractured. The crack has gone all the way through. I've created 2 pieces. And we actually map the actual surface area, not the projected surface area, but the actual surface area by using a laser scanning technique. And this is the kind of contour map that we generate. This gives us the actual surface area. Now, the actual surface area is plotted normalized to the the projected surface area. Higher this value, if the normalized area is 1, that means I'm creating a flat surface. As the normalized area starts increasing, that means I'm starting to create a lot of features, surface features, and it indicates a higher level of tortuosity of the crack. So if I look at this control concrete, the concrete made with a normal aggregate, I see that it has a normalized area of 2. That means the actual area that is created is 2 times the projected area. But as we start increasing the replacement level, we find interestingly that the surface area actually starts increasing, to the point that if I come to 100% replacement or concrete made with RCA, the actual surface area is higher than 2, which indicates a lot more surface is created. Now that's an interesting observation, and it directly goes into conflict with our previous observation, which indicated that the material was much more brittle. So we also looked at the fracture surface. If I look at the fracture surface in the control, this is concrete made with natural aggregate. We find that aggregate are literally pulled out of the fracture surface. So this is the concrete aggregate here, and the matching part of it on the matching piece, corresponding piece, is shown here. And you can see that the concrete appears like it's been pulled out of the motor surface. And this happens because the crack essentially grows in the ITZ, the interface between the new motor and the aggregate phase. And this is the kind of surface that we are getting. And we didn't observe any fractured aggregate on this fracture plane. But when we went to the 100% RCA case, that is, this is concrete made only using recycled concrete aggregate, we had some aggregate that were pulled out, but there were also some fractured aggregate that are present there. Some aggregates are actually fractured. Now, the motor strength is the same in both. So it is very surprising for us to see fractured aggregate on the fracture plane from a fractured test specimen. Now, so we took a piece of concrete that contained RCA. It was nicely polished and ground just to see the state of affairs. So here we see this is a piece of concrete. This is the RCA. So this dark here, it shows the RCA. This is the old motor, which is lighter than the new motor. So this darker shade of gray that you see here is the new motor. This is the old motor that is adhering to the aggregate phase. The aggregate phase itself is dark. What we found is that this new ITZ that is created between the old motor and the new motor is quite porous, as you can see here. It looks like water has accumulated here, and it looks like a lot of small, tiny pores are created. That is seen here. Further, we also saw some pre-existing cracks in the aggregate. So the aggregate phase itself contain cracks. These cracks were likely introduced during the violent production process of the aggregate. The concrete itself is hammered and then it is ground. So during this process, there are a lot of fractures that are introduced in the aggregate phase of RCA. So basically what we learned from here is that fracture in the normal grade concrete is concrete that is made for of 30 MPa compressive strength. The fracture in the RAC, the recycled aggregate concrete, is controlled by weak planes. So there are weak planes in the RAC, the concrete. The weak planes are in the ITZ between the new motor phase and the old motor phase. And there are weak planes also in the aggregate. There are these pre-existing fracture planes, which basically are also evident in the fracture surface that we saw. In the fracture surface, we did observe fractured aggregate, and that's because these aggregate were already cracked. So essentially, when the crack plane went close to it, the crack preferentially passed through the pre-existing cracks in the aggregate. And that resulted in a larger surface area and a more tortuous path, because the pre-existing planes, the crack planes in the aggregate, are not always perfectly aligned with the fracture, with the plane of fracture. So what happens is the crack actually takes a more detoured, tortuous path, because if this is a weak plane, the crack would essentially prefer to pass through here, and in doing so make the crack path more tortuous, and that creates a larger surface area. So these weak planes, while they contribute to surface area, do not contribute to energy because it doesn't take much energy to fracture along the pre-existing cracks. And we also saw a reduction in the tensile strength. So putting these things together, if I place recycled concrete aggregate in normal grade concrete, the inference I get is that it's easy to crack. It cracks easily because it has a lower tensile strength, and it requires lower energy for crack advance, and that is because it has all these weak planes, which basically the crack path essentially seeks these weak planes and travels along the weak planes. And in doing so, it creates a larger surface area. So the one way to mitigate this effect would be to strengthen these planes. And the obvious one to strengthen would be by taking care of this ITZ between the new mortar and the old mortar. And that can be done by densifying the ITZ, which is typical of what is done in high strength concrete. So in the next set of experiments, excuse me, we basically produce concrete of a higher grade. This is concrete with a characteristic strength of 50 megapascal. And the way that typically we produce higher grade concrete is by cutting back on the water to cement ratio and by inherently densifying the matrix. So for this the M50 grade concrete made with normal concrete, we achieved a characteristic compressive strength of a target mean strength of 57 MPa. And the same concrete made with RAC had a much lower compressive strength. Here is the fracture test response. And again, we see that there is a drop in the peak load. And if I calculate the energy, under this as a function of this crack mouth opening displacement, again, I find that there is a discrepancy, that the recycled aggregate concrete has a lower energy. Next, what we did was to look at the crack growth. How does the crack grow in this concrete? So here is a typical load response, the fracture test. I just wanted to show you some images along here. Now, we captured images and did an analysis using digital image correlation. So this is the analysis that we have from digital image correlation. Here is a typical image of a specimen with the crack, and over this area, if I plot the displacement, what we find is if I go across any line here, there will be a jump in the displacement, and that is shown nicely here. And you can see these are the displacements plotted in this whole area. So you see here is my crack, and the displacement discontinuity is very large at the mouth of the crack, which is this location here. So which is this here. And as I go up here along the crack, the displacement discontinuity decreases. So I can actually plot the displacement discontinuity along the length of the crack. And wherever the displacement discontinuity becomes 0, I can locate the tip of the crack. And as I plot the displacement discontinuity across the crack, I can also generate the crack profile. So at these 3 points, at point 1, 2, and 3, following this procedure, we have now developed the crack profile. So these are the crack profiles for this specimen. And at point 1, you can see this line here indicates the tip of the notch, and this is the opening displacement along the depth of the specimen. So the crack has just formed. It's in a very nascent stage at the peak load. And as I go into the post peak, you can see that the crack has propagated further. It has also opened further. The crack opening has also increased. Now, we've also done the analysis where we did the crack hinge analysis. From there, we extracted the tensile strength. So in the higher grade concrete, you can see that the tensile strength of normal concrete was 3.89, whereas the tensile strength of concrete containing RAC was 3.54. So the decrease in the tensile strength is a lot lower. Now, we also calculated the crack surface area, and we find interestingly here that the crack surface area is a constant. It doesn't change much with replacement of normal aggregate with RCA. So if I do a comparison between 0%, which is concrete made totally of normal aggregate, and concrete made totally of RCA, there is the surface area, the fracture surface area is almost identical. Now, using the information that we got from before, which is we have this information on the crack depth, how much has crack penetrated at different points in the load response. I can also calculate the energy under this curve, which is a measure of fracture energy. I can then plot the fracture energy as a function of the crack length. And that is done for different crack mouth openings. And what we find here, the solid symbols here are what we get from recycled aggregate concrete made totally of recycled aggregates. And the lines here are what we get from concrete made with natural aggregate. And if we find one is a nice R curve type behavior where the fracture energy increases and then eventually it becomes a constant. The other thing is that the fracture energy is almost similar or identical for both the concretes. So now when I go to a higher grade concrete, the difference that we saw before diminishes, and basically I get essentially a very similar fracture energy per unit crack length, and I'm also creating a similar crack area, area in the because of fracture. So coming to concrete made with RCA with densified ITZ. Densified ITZ is concrete made with a higher grade mortar. So fracture in RC in this particular concrete in with RCA is controlled by weak planes in the aggregate. Now the weak plane at the in the ITZ has been removed; it's been eliminated, and so the weak plane, the pre-existing cracks in the aggregate, these are the weak planes. Now, sensitivity to existing cracks in aggregate is decreased with the densification of matrix, and that's what we're seeing. So basically now both concretes are essentially behaving similar, and what we find is the fracture and crack propagation are nominally similar in concrete made with normal aggregate and concrete made with recycled concrete aggregate. So if I go to a higher grade of concrete. So coming to the last part of my talk, I want to see how this would influence the shear response of reinforced concrete. And for that purpose, we made this reinforced concrete beam, which had reinforcement, a flexural reinforcement at the bottom. And we also, this beam was tested in a 4-point test configuration with a shear span to depth ratio of 2.2. And on the one side of the beam, it was reinforced with stirrups to prevent shear failure, while the other side, there were no shear stirrups. So basically, this side would allow us to study the shear crack formation and help us understand what determines the shear capacity of reinforced concrete. So here are the test responses that we get from concrete made with normal aggregate and concrete made with recycled concrete aggregate. The difference in the compressive strengths are quite visible. As you can see, the compressive strength of concrete made with natural aggregate is 56.95. This is concrete that was proportioned for a characteristic strength of 50 MPa. Whereas when I do 100% replacement, the compressive strength decreases tremendously. However, if I look at the shear response, the peak shear capacity, which is this here, is nearly identical from both the concretes, the one made with NAC and the one made with RAC. Now, to figure out what is happening, we analyze the crack growth in the natural aggregate concrete. So this is basically the typical crack response, and I'm showing you the digital image correlation results at different points. So at this point here, these are the cracks that are formed. This is the part of the beam that did not contain shear stirrups, and you can see at this point pretty much flexural cracks are formed. Now at the peak load, this is in concrete made with natural aggregate. You see that another crack would have formed here, and that crack turns and becomes a shear crack. So you see this nice 45-degree crack that has formed here. The failure in this concrete was produced because of when the stress transfer across the shear crack essentially failed. So the shear crack was fully established, as you can see here. This is the load point, and this is the soffit of the beam. This 45-degree shear crack was fully established at the point of failure, and the beam actually failed when this the shear crack split open. That means the shear stress transfer across that shear crack could not take place, or essentially when the shear stress transfer failed, the beam failed. Now, looking at RAC, we find that if I look at the cracking at different stages, so this here again, you see the flexural cracks initially formed. One flexure crack forms and it turns into a shear crack. And at the peak load, again, we see that the shear crack is fully established. It's a nice 45-degree crack. And we find that loss of stress transfer across this shear crack is what produced failure. Now, when I have a shear crack that's formed, there is shear transfer that takes place across the crack. The two pieces of concrete that I have, which are separated by this crack here, will basically be functioning as one unit as long as there is shear stress transfer taking place across this crack. And when that gave way, the crack abruptly split open and the beam failed. The beam could no longer transfer shear force across the shear crack. So what we find is that when we compare the RAC and NAC, the shear crack pattern was identical, the mode of failure was identical, and now correlating it with what we observed in fracture test response, when I improved the grade of concrete, the fracture behavior was identical, the fracture energy that we had per crack length was identical, the surface area was identical. Now, the surface area, fracture surface area plays a very critical role in determining the stress transfer. So once a rough crack is formed because of cracking, so if I just go up here, if this is my shear crack and a rough crack is formed, and this crack itself is formed in mode 1, it basically is produced as a result of tensile fracture. And then what sustains the load is the roughness of the crack, the shear transfer that can take place across the rough crack. Now, rougher the crack, more stress can be transferred, higher the shear capacity. So what we find is comparing NAC and RAC in the higher grade of concrete, the surface areas that were created were essentially equal. The tensile strengths were also essentially equal, which means that the load at which this crack would form is also essentially similar. And therefore, we get the same capacity in shear. The formation of the crack, when it is fully established, happens at a nearly identical load. And because the crack roughness is also similar, the crack can only sustain so much shear stress, which is nominally similar in concrete made with NAC and RAC. So to conclude, with improving interface, if I improve the ITZ, my fracture behavior of concrete containing RAC, recycled aggregate concrete, is close to the concrete behavior that I get with natural aggregate. Similarly, the shear strength of concrete is also similar to NAC. Now, the differences are because the tensile strength is similar and the surface area created in fracture is similar. The compressive strength, what we find, there is a large difference in the compressive strengths that we get in the higher grade concrete when I replace natural aggregate with recycled concrete aggregate. And therefore, the compressive strength does not provide an indication of either the fracture behavior or the shear capacity. And it is essential to understand the fracture behavior to understand the shear capacity. So finally, compressive strength-based evaluation, which is commonly used in structural engineering practice, cannot be followed for the use of RCA in structural codes. So if we are going to adopt the recycled concrete aggregate in structural use, the existing models which are derived for natural aggregate and are based on compressive strength need to be revisited, and either they have to be recalibrated or a new set of models would have to be looked at. So with that, I would like to conclude my talk here and open the floor for any questions. Thank you. Thank you for giving me the opportunity to present here.